Hello, my name's Liz Hanbury and I'm a lecturer in pure mathematics at Durham University. I'm going to talk today about vector addition and scalar multiplication. And the plan is for this talk to be in 3 parts. So first of all, I'm going to talk about the basic definitions. Then we'll have a look at an example. And then finally, I want to say just a few words about how we can generalize these notions to higher dimensions. Okay, so we'll start off with the basic definitions. First of all, we're going to look at scalar multiplication. So I'm going to start off with the 2-dimensional case. And I'll begin by going through the algebraic definitions, and then we'll have a look at some examples and see how we can interpret this geometrically. So if I'm given a 2-dimensional vector, say u, which has components u1 and u2, and I'm given a scalar lambda, so remember that just means that lambda is just a number, then by definition lambda times u is the vector lambda u1, lambda u2. So when we multiply by lambda, we just multiply each component by lambda. So let's have a look at some examples. So here I've taken my 2-dimensional vector u, sitting here in 2-dimensional space, to be the vector 1, 2. And let's think about what happens if we multiply it by 2. So according to the definition we've just made, 2 times u should be the vector 2, 4. And we can see that multiplying u by 2 has had the effect of scaling the vector by a factor of 2. What about if instead we'd have multiplied u by a half? Well, according to the definition, a half u should be the vector a half, 1. And here it is. And we can see that multiplying by a half has had the effect of scaling our vector by a factor a half. What about if I'd have multiplied my vector u by 0? 0 is a perfectly good scalar, and the definition tells us 0 times u should be the vector 0, 0. This is what we call the 0 vector. It doesn't go very far, so I've just represented it here by a point. So we know what happens if we multiply our vector by a positive scalar, or by 0, but what about for negative scalars? So I could have multiplied u by -1, and that's going to be the vector -1, -2. And we can see from the picture that multiplying by -1 has had the effect of giving us the vector that points in the opposite direction. And similarly, if I'd have multiplied by -2, I would have got the vector -2, -4. So multiplying by a negative number gives you a vector that points in the opposite direction. And in general, then, we can think of multiplying by a scalar lambda as rescaling your vector by a factor of lambda, where if lambda is negative, we understand that we're going to get a vector that points in the opposite direction. Okay, so let's have a look at the 3-dimensional case. That's just entirely analogous. If I'm given a 3-dimensional vector, say v, that has components v1, v2, and v3, and if I'm given a scalar mu, remember that just means that mu is some number, any number, then by definition, mu times v is going to be the vector mu v1, mu v2, mu v3. So again, when we multiply by mu, we just multiply each component by mu. And in this case, in the 3-dimensional case, the geometric intuition should be exactly the same. So here I've got my vector v that's sitting in 3-dimensional space. And you can see if I multiply by 2, then I get a vector that's just twice as long and points in the same direction. And again, generally, we should think of multiplying by lambda as scaling your vector by a factor of lambda, where if lambda is negative, we understand that we're going to get a vector that points in the opposite direction. Okay, so now move on and talk about vector addition. So again, I'll begin with the 2-dimensional case. And we'll start off with the algebraic definitions, and then we'll see how to interpret that geometrically. So if I'm given two-dimensional vectors, say u, which has components u1 and u2, and v, which has components v1 and v2, then by definition, the vector u plus v is just the vector u1 plus v1, u2 plus v2. So again, this operation just works component-wise. To add my two vectors, I just add their components. So let's have a look at an example and see how we can interpret this geometrically. So here I've got my two-dimensional vectors sitting in two-dimensional space. I've taken the vector u to be the vector 2, 1, and v is minus 1, 2. Then according to the definition we've just given, the vector u plus v should be the vector 1, 3. And now we can see that going along the vector u plus v is the same as going along u and then going along v. So addition of vectors can be thought of as this top-to-tail composition of directed line segments. Okay, and what about in the three-dimensional case? Well, again, the definition's entirely analogous. So if I have a three-dimensional vector w, say with components w1, w2, and w3, and another one, say y, with components y1, y2, and y3, then by definition, the vector w plus y is the vector w1 plus y1, w2 plus y2, w3 plus y3. So again, vector addition is just done component-wise. And the geometric intuition should be exactly the same. So if I've got my two vectors w and y sitting inside three-dimensional space, then to form w plus y, I just add them together component-wise. And again, we can see that going along the vector w plus y is the same as going along w and then going along y. Okay, so we've seen how to define vector addition and scalar multiplication, and I'd just like to finish this section by mentioning a few properties that these operations satisfy. Now they satisfy lots of very nice properties, so I'm just going to mention a few of them as an example. So to start off with, if I'd like to multiply my vector v by the scalar lambda plus mu, this is always going to be the same as lambda times v plus mu times v. Okay, so this identity will hold for every scalar lambda and every scalar mu and for every vector v. So for example, 5 times v is always the same as 3 times v plus 2 times v. As another property, we have that lambda times the vector v plus w is always the same as the vector lambda times v plus lambda times w. So for example, 7 times v plus w is always the same as 7 times v plus 7 times w. And I'll just mention one more. So if we want to multiply the vector mu v by the scalar lambda, that's always the same as lambda times mu times v. So for example, 2 times 3 times v is always the same as 6 times v. Okay, so vector addition and scalar multiplication satisfy lots of properties similar to these. And these properties hold precisely because the operations of scalar multiplication and vector addition are just defined component-wise. So all we're really doing is adding and multiplying numbers. And because we have these identities and others like them, it means that we can manipulate equations involving vectors in much the same way as we would manipulate equations involving numbers.